Welcome to a little exertion of Riemann Hypothesis, an odyssey with the bonus of getting acquainted with anti-provability, something mathematically profound that may not make a show in a lifetime. Although distinctly unique, anti-provability can be easily confused with unprovability. The latter, as common knowledge, refers to a statement whose truth value cannot be demonstrated or determined, while the former represents the same quality but related to theory or proof. As pertaining to a conjecture, anti-provability must meet three conditions. It requires the posit to be true as a premise. It further requires a proof of general comprehensibility that is evident to math-oriented undergraduates. It also requires a situation created where the problem remains open long after being fully resolved. Here further clarification may need be in place. The incidents of Lobachevsky, Cantor, and Galois can be mistaken as instances of anti-provability, but their idea cannot be considered generally accessible at the time, whether due to the way the theory was conveyed then, or to the fact that the view was far ahead of its time. Since the current open status of Riemann hypothesis is virtually unchallenged and held absolutely unchallengeable, a proof long in existence is enough to satisfy all three conditions. So, let us have a proof. We are lucky to have somebody ask the question, why have we not solved the Riemann hypothesis yet? We can hardly see such a question aloud in math forums. Often ill-treated are such good questions that imposters have to expressively dismiss in order to hide their incompetence at finding out the reason that can possibly turn out to be a prerequisite for the proof. The largely informal proof presented here gives details about the reason mathematically. With the proof, however, anyone may also be able to make it clear, in non-mathematical but unequivocal terms, why we keep failing so successfully. And thanks to the question, we can take the opportunity to exhibit a proof of Riemann hypothesis, to expose the reason, which is generally seen as unattainable, even if we can finally prove. Unless a mathematical exposition is on hand, any attempt at addressing that question can turn out to be pregnantly vacuous, with verbiage that the crowd mysteriously find palatable. Yet an actual reason, though mathematical in nature, may require no math background to understand. The reason we have failed in the attempt to settle Riemann hypothesis for such a long time is that we have been fixated on the futile line supposed to contain all non-trivial zeros. If we try dealing with Riemann hypothesis by looking at lines that are not vertical, that is not orthogonal as the critical line is, to the real axis, the situation can be drastically different, but we then will need, of course, to render Riemann hypothesis slightly differently in an equivalent statement as follows. Any line not perpendicular to the real axis can contain at most one non-trivial zero of the Riemann zeta function. The question of whether Riemann hypothesis is false or true is equivalent to the question, can or cannot a line unorthogonal to the real axis contain two non-trivial zeros? Were there a non-trivial zero x off the critical line, we could pick any non-trivial zero y on the critical line and let a line pass through x and y, resulting in a line not perpendicular to the real axis containing two non-trivial zeros. Therefore, having a non-trivial zero off the critical line is equivalent to having some non-vertical line passing two non-trivial zeros. On the other hand, if no non-vertical line can contain two non-trivial zeros, in other words, any such line contains either just a single non-trivial zero or none at all, then only a vertical line that is the line of symmetry can contain more than one non-trivial zero, which is equivalent to the version of Riemann hypothesis we universally preach. Therefore, if we can prove that any line not perpendicular to the real axis can contain at most a single non-trivial zero, Riemann hypothesis is settled. Of course, We can pick lines of any non-vertical slope, but, obviously, the most desirable are lines horizontal that is parallel to the real axis. If there were two non-trivial zeros on that line, they would be off, as well as symmetric to the critical line. If there is only one, then the symmetry will force it onto the half line. Let G denote a horizontal line, where G can also be regarded as the set of all points forming the line. The proof is to take any horizontal line G that contains at least one non-trivial zero and show that there can be only one for that line. The way to achieve this is to show that the points in G form an additive group G with operator O+, and being additive, group G is structurally the same as the additive reals, with group G being isomorphic with group R. It is a known fact that any subgroup of additive reals is either infinite in size or finite with size 1. In other words, the only finite subgroup of the additive of reals is the singleton group containing the identity 0 of R. So both being additive and infinite, or infinitely cyclic as we conventionally term it in mathematics, group G has the same property as group R, with subgroups of group G either infinite in size or of size 1, where the latter size indicates a single element of set G, the identity of group G. With G as the domain of zeta, instead of the entire complex number set C, consider K, the collection of all non-trivial zeros in G mapping to 0, the identity of the group of reals. K forms kernel, which is group, with group K being subgroup of group G. Since G, a non-vertical line, will have to intersect the 0 line and the 1 line which mark the boundaries of the critical region, G cannot have infinite number of non-trivial zeros, because non-trivial zeros won't appear beyond the 2 points of intersection, as being beyond means being outside the critical region. So all non-trivial zeros will be within the line segment between the 2 points of intersection. As any horizontal strip in the complex plane with finite height can only contain finite number of non-trivial zeros, a strip containing the line segment will force the segment to have only finite number of non-trivial zeros. Therefore, K subset of G can only have finite number of non-trivial zeros, but when such additive group K, subgroup of group G, is finite in size, it can only contain a singleton, just as the only finite subgroup of the additive reals does. As K, the non-trivial root set of G, contains a singleton, Riemann hypothesis has to be true. We recapture and summarize this episode here. Riemann hypothesis is settled when we prove, if any line parallel to the real axis contains non-trivial 0, it contains only 1. Under the light of the proof, the reason for why have we not solved the Riemann hypothesis yet is quite clear both within the realm of mathematics and beyond. It is quite obvious that true progress, partial or complete, should be able to tell the reason. A claimed proof, or some believed breakthrough, however celebrated, having no clue of the reason offers only vain grandiosity, and will have hardly anything to contribute to the final settlement. Having come thus far to this point, the reader sees, at a minimum, a complete exposition. Following this verbal presentation, there will be several screens of silent text, with the same algebraic proof but different and somewhat more formal explication, more or less reflecting a roadmap from an initial idea to the final settlement. In the description section, there are also pointers to answers offered to some of the various related curiosities and issues raised over time by people, as well as a link to the initial idea in the form of a question about exploring lines other than the one the world got addicted to.